Hello and welcome to Tech Decoded. My name is Henry Gabb. I'm the editor of the Parallel Universe, Intel's quarterly magazine devoted to software innovation. Today I'm talking to Larry Meadows, a senior principal engineer in the Intel Data Center Group. Larry's been doing high-performance computing since 1982 when he was writing assembly code for array processors before moving into compiler engineering. Today, Larry works on performance tools and analysis tools for present and future Intel architectures. So welcome, Larry.
Thank you.
So modern processors require modern coding techniques. And I keep hearing vectorization and threading for code modernization, but these techniques have been around for a long time. So what has changed?
Pervasiveness is the key. Originally, vectors existed on big vector machines like Cray and NEC machines in the late 70s and into the 80s and 90s. Now, every microprocessor from every vendor has what we call a SIMD unit, single instruction multiple data, that it allows to do multiple operations in a single instruction. Typically floating point, you can do 2, 4, or 8, or even 16 single precision adds at the same time. That feature is on every processor in almost every device you use. So it's in your cell phone, it's in your laptop, it's in your tablet, and it's in the server that you rent from Amazon, for example. Threading is similarly pervasive. Even a single core Intel CPU has 2 threads on it, and most CPUs have. My Mac has 2 cores. The bigger Mac has 4 cores. So if your software wants to, you as a software vendor want to make the best use of modern CPU, you have to both vectorize and parallelize it.
Right, even edge devices nowadays have multiple physical cores.
That's right.
And even a single core machine will have hyperthreads.
That's right.
So back in the day, though, if you wanted to vectorize or thread code, each vendor had its own set of directives or its own libraries for vectorization and threading.
Right.
So what programming models today support vectorization and threading?
So OpenMP arose. OpenMP is a standard. It's not an ANSI standard, but it's an industry standard. There's a standards body that produces new versions of it regularly. It grew out of the need to unify the threading directives that you mentioned. There were at least 4 or 5 different versions that I remember, and probably more that I don't. Threading, so that's threading. Now vectorization never had a standard. Typically the compiler does the hard work for vectorization. You don't have to write assembly language these days, but there may be something you need to tell the compiler, some sort of a hint or a directive saying it is in fact legal to vectorize this loop. And relatively recently OpenMP has standardized the spelling for that pragma as well. So the compiler and the runtime using OpenMP will do the heavy lifting for you, and you simply have to add some directives. We also have alternative threading models, which we can talk about, threading building blocks, for example.
Well, I remember the old IVDEP pragma that's still around after probably 40 years, 30, 40 years.
Something like that.
Because
yeah.
the compiler is always conservative.
Right.
It has to be conservative
Right.
about your intent.
Right.
And so that old directive, you would tell the compiler, it is safe to vectorize this code, even if it's not clear. But you're saying that OpenMP has standardized those directives for vectorization as well as threading.
That's correct, yes. So you can tell the compiler pound pragma OMP SIMD, which means it's okay to generate SIMD code for this loop.
Okay, because I remember when OpenMP came on the scene, really 20 years ago, over 20 years ago when it came on the scene, to unify all the different syntaxes for compiler-directed threading. It gave me a way to describe the parallelism to the compiler, and the compiler would implement it.
That's right. In the old days, you might have either used a proprietary directive or you might have written p-threaded code. P-threads is the assembly language, if you like, of parallel programming. OpenMP still uses p-threads, but that's done by the compiler and by the runtime, not by you. So you don't have to do anything except, say, execute this loop in parallel.
So the compiler can do a lot of the heavy lifting for vectorization and threading now.
Okay. Yes, correct.
So there's a spectrum. Okay, I like to think of a spectrum of developers, and at the one extreme there are people like me, the application developer, the domain expert who's just trying to get a result. And over on the other extreme, where you live, are the tuning experts who want to extract every ounce of performance out of a piece of code. You pay attention to how the code will interact with the compiler and with the actual hardware.
Right.
So there's this separation of concerns and this big gap between the domain expert and the tuning expert. What is Intel doing to bridge that gap?
Lots of different things. Starting at the very top level, you have a code and you don't even know whether it's legal to parallelize it or where, or whether it's legal to vectorize it or where it will be helpful. So we have tools to determine the vector advisor, and parallel advisor will tell you whether or not loops can be vectorized, whether or not it's profitable to vectorize them or parallelize them, and help you insert the directives to do it. Once you've got some parallel code, you've got some vector code, we have profiling tools like vtune, which will tell you how well the code is using the machine. Maybe you parallelized a loop, but it was only executing 10 iterations, right. And so you're only using 10 threads, and so it's inefficient. So you might have to move your parallelism to a higher level. We have libraries that embody optimal algorithms that are both vectorized and parallelized that you can use.
Mm-hmm. So there are tools to help tune the code that I write. What about raising the level of abstraction?
Well, libraries are one way to do that, and libraries are getting more and more sophisticated. So we've always had the traditional fast Fourier transforms and linear algebra kind of libraries.
And matrix multiply.
And matrix multiply, yeah, dense linear algebra. We've also got sparse solvers, that sort of thing. As software evolves and gets more and more complex and more functional, the level of the libraries tends to evolve as well. So for example, we have recently a library for MKLDNN for AI deep learning, and also we've got data analytics libraries, that sort of thing. So that's one way to raise the level of abstraction. Another way is domain-specific languages or frameworks, where you maybe write some stuff in Python and glue it together, and the implementation of that is where you get your performance.
Right. My goal ultimately is not to have to write code at all, to program with blocks and arrows. Essentially, I want to describe my workflow and have the runtime sort it all out.
Right.
So each box would then be some library routine that an expert has written and tuned, and all I'm doing is describing the data flow.
So in fact, we have the addition to a threading building box called TBB flow graph, which does precisely what you describe. You describe a set of operations and what their inputs are and what their outputs are, and the runtime is responsible for executing as much of that in parallel as possible and inserting synchronization where it's required for correctness.
So vectorization and threading, we're come full circle now, back to vectorization and threading. They've been around for a long time. Code that was vectorized 20 years ago is still vectorized today and will still perform well today. Code threaded 20 years ago is still threaded today and can take advantage of the architecture. Future-proof techniques, they're likely to still be valid 10, 20 years from now.
Right.
But new architectures are coming out, new hardware is coming. What do you see as the next evolution in code modernization?
We've got a number of different things. The first is we've already alluded to, which is using frameworks or other sorts of TBB flow graph to glue bits of optimized code together. Currently, often those optimized fragments are developed by different people who may not even talk to each other, different groups, and they may not interoperate well. For example, they may two different modules may assume they own the whole machine, and therefore they, when they both try to execute at once, they step on each other's toes. So composability is very important. More implicit parallelism is kind of the same idea. With TBB flow graph, you're just saying, here's my problem, you go find the parallelism. You know, but in general, you want to expose as much parallelism as possible and then try to get the compiler and the runtime to deal with it. So vectorization is an example of implicit parallelism. We're seeing more and more of that with things like TBB flow graph and even some OpenMP concurrent and C++11. And then both of those are really about raising the abstraction level that we've talked about. So more and more, you can do more and more with less and less programming. And the move toward using Python as a domain-specific language for lots of different areas is a big example of that. Intel's on top of all of that.
Great. Well, thanks, Larry, for giving us your insights on code modernization and its impact on developers. I'm Henry Gabb for Tech Decoded. Visit our website for more webinars on software tuning and optimization for Intel architectures.